Welcome back, ChemStars. It's time to go over Gay Lussac's law, which is where we're looking at the relationship between pressure and temperature. So think about what Mrs. Van de Walle showed you with the PhET simulation, and imagine if you're a moving molecule. If you're stuck in the same room, and all of a sudden you start walking faster and faster and faster, you're going to collide into each other and the walls a lot more often. So if temperature goes up, that means pressure will also go up. Let's think about it another way. What if you started walking really slow? Same number of people in the room, same number of gas particles, same volume. So if you walk slow, temperature goes down, and your number of collisions, your pressure will also go down. So as pressure goes up, pressure down, temperature down, they are a direct proportion. They are directly proportional to each other. Mathematically, that gives us this. So pressure 1 over temperature 1 equals pressure 2 over temperature 2. But remember, just like our other laws, we can't divide by 0 or by a negative. We have to go to Kelvin. So remember, Kelvin, we have to add 273.15 to those degrees Celsius. And it's just kelvins, but it's degrees Celsius, degrees Fahrenheit. Okay, so let's go through a couple of these problems. A sample of neon, a neon gas, is at a pressure of 2 atmospheres. So let me try and color code this for us. 2 atmospheres, so this is pressure 1, and it decreases to 1.2 atmospheres. That's pressure 2. If the temperature starts at 0, now I have to convert that to Kelvin, remember. What will the final temperature be? So T2 equals question mark. Okay, so very important to go through and kind of diagram that in the problem so you know what you're being asked. So pressure 1, fill in, is 2 atmospheres. And temperature 1, we can't put in that 0. We've got to put in 0 plus 273.15, which gives us 273.15 Kelvin. Don't round for sig figs yet. Keep that until the end. Pressure 2, we're told, is 1.2 atmospheres, and temperature 2 is an unknown. Before we start, we want to make a good prediction of the answer. So pressure went from 2 to 1.2. Pressure decreased. The other key word we have right here is that it actually tells you it decreased. So if pressure decreases, and we know that pressure and temperature are directly proportional, what do you expect will happen to the temperature? Temperature should also go down. So we should see a decrease from T1 to T2. Now, before you start, always write that original equation. Then we're going to substitute, do some algebra, get a calculator answer, and round it for our sig figs. So pressure 1, we want to fill that in, plug in and chug through the math. 2 atmospheres. Temperature 1, 273.15 Kelvin. Pressure 2, 1.2 atmospheres. Temperature 2 is unknown, we're solving for it. Now we've got to do some algebra. You can cross multiply and then divide out, or just bring T2 up to each side, divide out the 2, multiply with 273.15, whatever you want. You'll get the same answer as long as you do your algebra 1 right. So here's what the algebra should look like. Here's what we should be entering into our calculator. Let's do a check. 273.15 times 1.2. Let me get this right here. Okay. And then divide by 2, we should get 163.89. Yep. Okay, but now we need to do our sig fig check. Now, we got the problem in Celsius. We probably should report it back in Celsius. So if we have 163.89 Kelvin, subtract the 273.15. There's a point there. It doesn't really show up. And here's our Kelvin answer. Here's our Celsius answer. Now we want to round it to our correct number of sig figs. Okay, look at the original problem. 1, 2, 2 sig figs. 1, 2, 2 sig figs. Don't worry about the sig figs here because technically it's 3 from adding the least number of decimal places. We want to go to 2 sig figs. I did not do that here. Let's fix it. I went to 1 from the 0 Celsius. So we actually want to have 2 sig figs, 2 sig figs. Technically, it's our least number of decimals once we've added, so there's 3 sig figs. So let's go to 2. 1, 2. So look to the right. This is going to be 160 Kelvin. 1, 2. This is going to be 110 Kelvin. Those are the right answers. Don't get too messed up with the sig figs. Just go with it on that one. Did this change as we predicted? We predicted that temperature should go down. We started at 273. we went Kelvin, we went to 160. That went down. Or we started at 0 Celsius and we went to negative 110 Celsius. Oh, geez, I'm just struggling here. That should be Celsius. Oh, boy. There. Now that's right. So did it change as we predicted? Yes. Once I put the right unit and the negative sign there, it was fine. Okay. Problem 2. Problem B. The temperature of a sample of gas starts at negative 250. So if we're starting at negative 250, this is temperature 1. We've got to convert that to Kelvin. And it's warm to 40 degrees Celsius. This is temperature 2. We also have to convert that to Kelvin. The final pressure, oh, now I'm getting all off with my color coding here. Let's make that correct. T2. The final pressure, P2, is 760. That should be familiar. That's standard pressure. That's 1 atmosphere. What is the beginning pressure? So what is the beginning pressure? Pressure 1 equals question mark. That's the initial diagramming you want to do every time. Identify what you know, what you're given. Try and keep them all separate from each other. So pressure 1, we don't know it. We're solving for it. Temperature 1, we have to convert that negative 250 to Kelvin. To take your negative 250 plus 273.15, we've got 23.15 Kelvin as initial temperature. P2, we're told, is 760. At this point, note that there's 2 sig figs here. There are technically 3 sig figs here, least number of decimal places after adding and subtracting. And T2 is 313.5 Kelvin. So look at the temperature. Did it go up or down? Temperature went up. The other key word you have is that it warmed, so temperature went up. Do you expect pressure to go up or down? They are directly proportional. It should do the same thing. So first things first, we always want to write the original equation. Do not skip that step. Write the original equation. Don't confuse it with Charles or Boyle's and write the wrong equations here. Pressure 1, plug in and chug through the math. Unknown. Temperature 1, make sure we're putting in that Kelvin, never Celsius, never Fahrenheit. Pressure 2, 760. Temperature 2, 313.15. You can cross multiply and divide to isolate, or isolate and solve for pressure 1. Just do your algebra correctly, and we're going to get this. This is what we're typing into our calculator. We've got 23.15 times 760 divide by 313.15. We get 56.18. Okay, can I do this right? 56.18 millimeters of mercury. Now go back to the original problem. 2 sig figs here. Technically, we ended up with 2 to then also 3 sig figs in the temperatures. Keep it to 2. That's our least number anyways, no matter how you look at it. So 2 sig figs, 1, 2. Look to the right, 1 won't round the 6 up. 56 millimeters of mercury is my final answer. Now we got to do our check. We predicted that temperature went up, therefore pressure should also go up. Pressure started at 56, went up to 760. Yes, it looks like everything went right. So we are all good. Good job, guys. I'll see you next time. Don't wait to be great.